Okay. Well then, welcome everybody to the seminar Algebraic and Combinatorial Perspectives in the Mathematical Science. So I'm Moritz Weber from Saarbrücken. I'm co-hosting today's session. And today's speaker is Karin Baur from Leeds. She did her PhD 2002 in Basel and then had several positions. And since 2018, she's in Leeds. And her talk today will be Friezes in algebra and combinatorics.
Thanks a lot. Yeah, I want to talk about several aspects of Friezes, mainly of integers. And apart from the Frieze groups, which were studied longer ago already, Frieze patterns of integers have first been introduced by Coxeter in 1971, and then studied by Conway and Coxeter in the 1970s in two very nice papers. So the first one just gives some 30 problems, and the second one gives hints. So the idea is that you solve these problems yourself. The main theorem of these two articles is going to be the Conway-Coxeter Frieze, which I'll present in a few slides. So these patterns can be realized via triangulations of surfaces, and since triangulations of surfaces are linked to cluster algebras and cluster categories, the interest in these Frieze patterns was renewed around 10 years ago. And since then, there has been a lot of activities. Let me first explain what a Frieze pattern is, how Coxeter first introduced it. So this is a grid of numbers or elements in an integral domain, as here. So you start with a row of zeros, and then you shift a little bit, put a row of ones, and then you shift back and start putting unknown entries. So these A, I, J are in R non-zero or in an integral domain. Mostly today they're going to be integers, positive integers, but at some point I'll use cluster variables. This is known to be coming from an integral domain. So there are two rules basically, and an extra one for technical reasons. So the first one is the so-called diamond rule on these grids or lattices. Whenever you see a little diamond or square like this in the pattern, then you ask that AD minus BC is 1. So you could also call that an SL2 rule or Frieze. And there have been SLK Friezes considered since, so it's a very nice generalization. Then there's a periodicity asked, so it means that you have a translational symmetry as in a Frieze in architecture. So there should be an integer n positive such that when you go n steps to the right, you repeat the entries. And then the third condition is tameness, is that whenever you take a 3x3 diamond or matrix, that the determinant is 0. So that will prevent us from getting zeros somewhere in between. And it means that basically the first row of non-trivial entries determines the rest of the Frieze. Because you can start using the diamond rule and you never have a problem with dividing by 0. Okay, so that's the basic setup. I said mostly we're going to specialize and look at integers. So that's the notion of an integral Frieze. All non-trivial entries are positive integers. I'm sorry, that's the dishwasher. Closed Friezes means that these Friezes end. Sorry. Closed Friezes means that this process, like you see here on the first page, I put ... but that it ends at some point. So closed freezes are freezes where we end with a row of ones and a row of zeros. In that case, the order of the frieze is the number of rows minus 1. So this is the number of non-trivial rows plus 3. There are different conventions here. Sometimes the number of non-trivial rows is the order or the width, but I'll stick to this one because it fits nicely with the triangulation picture. Then the quiddity sequence. So as I mentioned on the first slide, this row here, the first non-trivial row, determines the rest of the frieze. And quiddity sequence means, quiddity means the what if and what isness or essence of a frieze. And that's a word introduced by Coxeter. Is the first non-trivial row, but now we remember we have a periodicity, so we just take any n successive entries there. If we have period n. And then fundamental domain in closed friezes. Let's wait for a bit before we have the first example of a closed frieze. So a closed frieze of order 6 here. I can use my diamond rule, and I know that 2 times 1 should be 1 more than 1 times something. So here I get an entry 1. In the next diamond, 1 times 4 should be 1 more than 1 times 3. And then I'll end this a bit more quickly. The third non-trivial row will have 1 times 3, so it's 2, 2, 2, 1, 4, 1. And then you should see that we get back to ones and zeros. So we have a quiddity sequence or row here. It has period 6 and order 6. What else did, now I want to illustrate the fundamental domain. So what you can observe is that there's actually a triangular region which repeats. So if I go 1, 1, 3, 2, 1, and then I go up again. So this triangular region is used to fill the whole frieze by doing a glide reflection. So it's a triangular region. And these closed friezes have a glide reflection, as we'll see in a minute. Okay. Good, so these are the most important words for now. As I said, we'll mostly talk about integral friezes. And one of the reasons is that they have a nice geometric interpretation. So we can find triangulations of polygons for these closed friezes or triangulations of annuli for infinite friezes. So when we never stop. Okay. So the closed friezes are mostly studied in this paper by Conway and Coxeter. And the theorem is that there is a bijection between frieze patterns of order n and triangulations of convex polygons, of a convex polygon with n vertices. So as I said, we're looking at integral friezes. All non-trivial entries should be positive integers. And then we can think of them, these entries, as counting something. So that's the matchings, as we'll see. And the idea behind this is that you look at the convex polygon with n vertices 1 up to n. And you take a triangulation of that. So this is the idea how to go from a triangulation to a frieze. And the triangulation is a maximal collection of non-crossing diagonals only between the vertices of the polygon. So once I have a triangulation, I put an example here, I can count triangles and I let AI be the number of triangles at vertex I. So in my example here, I find 4 triangles. A2 is 1, A3 is 2, A4 is 2, etc. And then what you prove is that this tuple of positive integers is the quiddity sequence of a closed frieze of order n. So that would be one way, one direction in this projection. Then just to give some idea how one could prove this, there's the key ingredient that you can go between quiddity sequences with n elements and quiddity sequences with n plus 1 element by gluing and cutting. And the gluing procedure is if I have a quiddity sequence and I can insert a new entry between 2 consecutive entries. So insert and increase. As you see here, I introduced a new entry between AI and AI plus 1, but I also have to increase these 2 entries. And this is called gluing because on the polygon side, it means you glue a new triangle between vertex I and I plus 1. To the polygon. Then cutting is the reverse procedure. If you have a quiddity sequence where you find an entry equal to 1, then you can remove it and decrease the 2 neighbored entries. So that is remove a 1, an entry equal to 1, and that means remove a triangle from the triangulation. And by doing so, decrease the polygon. So these are the main ingredients, and then you can prove the theorem by induction on the number of vertices of the polygon. So there are a few immediate consequences. First of all, the order is like almost equal to the period. In fact, it is a factor of the period. Because sometimes your triangulation can be very symmetric and then you have a smaller period. Then there is these ones in every quiddity sequence. There are at least 2 entries equal to 1, which comes from the fact that we're dealing with triangulations of polygons, convex polygons. They have at least 2 exterior triangles. We call them ear. And the last consequence is that you never have 2 neighbors which are both equal to 1. I should say 4. And at least 4. So these are the main properties of integral closed friezes. Then a little bit later, Broline, Crow, and Isaacs looked at all, and we have a geometric interpretation of the first row because the quiddity sequence counts matchings. But in fact, you can look at all entries and view them as matchings, and that was shown by Broline, Crow, and Isaacs in 1974. So if I remember, like there is, for a Frieze of order n, there is a triangulation of a polygon, and then I can look at incidences between triangles and vertices. So instead of just looking at the vertex and count the number of triangles, I look at the sequence of vertices and try to match triangles to them. So these are matchings between vertices I plus 1 up to j minus 1, and I call this set curly mij. And what Proline, Crow, and Isaacs show is that the entry aij in the Frieze is given by the matching numbers, and it's symmetric in the index set. So let's just look at one example. I take my triangulation from before, and for example, A13, I should count the ways to allocate triangles to the vertex 2. There's only one way to do this, and so the number is 1. And I should write this number 1 in the Frieze, A13. Then if I want to find out the number for 36, well, then I have to look at allocating triangles for vertices 4 and 5. So in position 4, I could have delta C, and then in position 5, delta B, or delta C with delta A, or delta B with delta A. So these are 3, and then A36 is 3. And then we have repetition. And then you can fill this out, and you should recover the same Frieze as before. Okay. And then one last result from that paper of Proline, Crow, and Isaacs is that you can attach to the Frieze a determinant in the following way. So if I look at the Frieze pattern, which is closed, then I know there's a fundamental domain, like this, for example. And I can take this as the upper triangular part of a matrix. So I've put that here. And then I want to make it symmetric, so I just take another copy of the fundamental region, identify the zeros, and glue this together to make a square matrix. And if I compute the determinant of this matrix in the example, this is -4. Or in general, if I have a Frieze of order n, then I define the matrix of the Frieze to be given by exactly these numbers in the fundamental region, make it symmetric, and get a symmetric n by n matrix. So then what you can show is that if you have a Frieze of order n with matrix M of f, that the determinant is independent of your choice of Frieze or triangulation. It's always a power of 2 up to sign. And that's relatively easy to show. You find an entry 1, and you do a row column reduction, and so that you have an entry 2 on the diagonal and make it smaller. And you do it iteratively, so you get a 2 every time, but then you have a sign. Okay. So very quickly, for anyone familiar with cluster algebra, so there are versions of these Friezes in cluster variables. And because it is known that polygon triangulations lead to cluster algebras of type A, where each cluster variable comes from a diagonal of the polygon, and you use Ptolemy relation to get to a cluster algebra. This is not going to be important for the rest of the talk, but it's just as a side remark. So we take a cluster algebra of coming from a triangulation of my polygon Pn. The diagonals correspond to variables, which I index by endpoint, cluster variables. And then I also need the edges, which will just be xi, I plus 1. They are coefficients or frozen variables. And then the cluster algebra with its variables looks exactly like a Frieze we've just seen. Instead of the integers, we have the cluster variables in the positions indexed as before by Aij. So again, I get the fundamental domain and I can form the matrix now depending on the fundamental domain in variables. And what we can show is that the determinant is also a power of 2 up to these frozen variables of the boundary segments. And once you have that, you can specialize a cluster to 1 and you get an integral Frieze and all its properties, or the Frieze determinant of Proline, Crow, and Isaacs. Well, there is also a cluster category counterpart to that, which we study in that paper. Okay. So this is all about finite Friezes, but I want to talk about infinite Friezes as well. So now we sort of know that the finite Friezes come from triangulations of polygons, and so you have an understanding of quiddity sequences, but we also know that there are infinite Friezes. And the first example was already in the original paper by Conway and Coxeter. So in their problem 16, they put this Frieze, which starts with all 2s. And then you see, you get all 3s and then all 4s. And that's definitely increasing forever. It's never going to stop. So the question is really, can we characterize quiddity sequences which yield infinite Friezes? And that's not so obvious still, but we can give each infinite Frieze again through a triangulation of some surface. So what we can do as a first approach to this is that we consider a punctured disk, again with n vertices 1 up to n and 1 interior point, and you triangulate that. So as an example, I took n equals 5, and you see that triangulations now is not by straight lines, but it's easy to understand how this works. And I have to say how we get a quiddity sequence from that. It's a little bit tricky. So what we have to do is we have to look locally around each of the vertices. And we look at connected components of the complement of the triangulation. So I count, and let me do this really big. Near vertex 1, I count 1, 2, 3, 4, 5. And here I count 2, and then 2, 2, 1. So you see, the problem here is that we are overcounting some of the triangles. because I'm looking at the neighborhood. For example, this dot and this dot come from the same triangle. But I have to do this. That's the way it works. In the example, I should get 5, 3, 2, 2, 1. And then what Chapel showed as an answer of question how you get quantity sequences for infinite Friezes is whenever you take a triangulation of Sn, the matching numbers that I just defined, they give an infinite Frieze.
There's a question in the chat.
Yes.
So the question is it the number of angular sectors at the vertex?
Angular sectors is, I think it's one more. I don't know what an angular sector is. No, I think that's what you mean.
Sorry, I mean you just really ignore everything belongs around the little circle and.
Yes. Yes. True.
Thank you.
Yeah, so one could do the same in the polygon case because then the overcount just doesn't happen. It doesn't matter. That's a good point. Okay, so what she showed is that if you do that, then Q is the quiddity sequence of an infinite Frieze. Say f of Q, and all entries of f of Q are matching numbers in the same sense as before, but with this angular sector. I think that would make sense. The idea how to do that is you take a universal cover of that surface, you take a strip. It's not just a covering of the surface with a strip, and then you have to count matchings. That works exactly in the same way as in the finite case. And as a remark for this example of Conway and Coxeter, you have a much easier triangulation. You take a star, any star triangulation. So everything which has only diagonals to the center. Okay, so that's good, but it's easy to see that this doesn't give all the infinite Friezes. And let me remind you, we always assume periodic. So there would be more Friezes if we allow like arbitrary Friezes, and we could also give an interpretation of those, but I will ignore them for today. So there are other infinite Friezes, and we can give geometric interpretations for them. We use annuli. So we take a disk and we cut out another disk, and we consider triangulations of such a surface with points on both boundaries. So what we can prove is that every infinite periodic Frieze arises, and again, it's integral always, unless I say otherwise, every infinite periodic Frieze arises from a triangulation of an annulus. All entries are matching numbers for one of the boundaries of the annulus. So even this case, which Chabold had found, is a special case of that, of the annulus. So to view the Friezes from Sn, you think of contracting the inner boundary to a puncture or mark to the point. And then you get a result.
So I have one frieze here which is 3 periodic. The critical sequence is 2, 3, 3. And then you see, in contrast to the one by Conway and Coxeter, these entries grow really fast. And I've drawn a triangulation for that sequence. So we had Q 2, 3, 3, and you find 2 triangles, 3 and 3. You see that there is another frieze, which I'll ignore for the moment, because you could also count at the inner boundary. But for now, we were happy to find a geometric realization, also in the same way as in the finite cases. So the observation that these entries grow really fast brings me to the last part, the growth of friezes, integral frieze patterns. So we sort of have either a dichotomy or trichotomy. We have the closed friezes. Well, because they end again, entries in each, say, diagonal of the pattern grow for a moment and then they decrease. And you could, if you wanted, extend the frieze pattern just by mirroring it. Like I do a really small one now, n equals 4 from a quadrilateral. So I could just extend it by putting everything negative on the other side, and then grow. You can fill the whole plane by that, and then the numbers grow, decrease, and it continues doing so. So that's one side. And then if we take friezes from a triangulation of Sn, then it is a theorem by Chubold again that the entries in each diagonal grow linearly or form n arithmetic progressions. I'll illustrate that on the next page. And then, well, we have the third case. If we have something which comes from an annulus but doesn't live on Sn, then the entries grow exponentially, as we'll see. Okay, so let's look at the 3 cases. The first one is an order 5 pattern, which is finite. Then I have an infinite one, which comes from a triangulation of Sn. I've had that before, so the period I choose is 3. And the next one is coming from an annulus and doesn't live on the punctured disk. Again, of period 3. So what we were able to show is that when we have an integral frieze, which is m periodic, it could be finite or infinite, then whenever we go m rows down and look at the position straight north, these differences between the entries are constant. So let me illustrate that. Well, first of all, I have to say what is row 1 for this count. and maybe concentrate on k equals 0 first. So we have row 0, and then we extend it with a row -2. Well, then clearly the difference between 1 and -1 is always 2. So there's nothing interesting happening here in all three types. But if we go to the first interesting case is when k is 1. And here we have period 3. So I have to go to row 3, 1, 2, 3. And then the difference, 3 minus 1 is 2. 5 minus 3 is 2. 5 minus 3 is 2. The same in this other example. We have difference 10, 10 throughout the pattern. And I can do one more step, so 6 minus row 4. Well, the difference here is 2, 2, and 2. Whereas on the other side, when I go to row 6, I think the difference is, what is it, 102. Constantly. But this was really surprising. If you go to any other two rows, you see that the differences are never constant. Okay, so the case k equals 0 was clear. Now if we go to the finite Friezes, if the order is m equals to n, the period could be smaller. But let's say we look at period equal to the order, then if I put k equals 1, what I'm looking at is ai, I plus n plus 1. We're reducing modulo n. This is ai, I plus 1. This is again in the row below the whole Frieze. And I would have to look at the difference between that and ai plus 1, I plus n. And here we are in the row just above the zeros. The entries are 1. And so the difference is -2 constantly. Again, before I go to this graph a bit more, let me recall I said there were arithmetic progressions. In the diagonals in the punctured disk case. So for example, if I look at this diagonal here, given by 0, if I go 3 steps down, I get to 2. 3 steps down, I get to 4. And 3 steps down, I get to 6. So this is this linear pattern. You can do one more. For example, here, 3 steps down, plus 4, plus 4. So this is that result of Chabot, which I had mentioned in remark 2 here. Okay. And now that we see that we have these constant differences, we can fix the smallest possible of them. So S bar is going to be this difference, the first one, which is not the trivial one. So we take the minimal period of the Frieze and we look at these differences. In the middle example, S bar is 2. in example B. And S bar is 10 in the last example. In the first example, it's just -2. So we need this S bar as like an invariant of the Frieze. And then also we look at the whole sequence of differences, Sk. I've just copied the Frieze pattern once more. So the sequence of SKs in my punctured disk example is constantly equal to 2. And the sequence in my last example grows much more. It grows, in fact, is 2, 10, 102, etc. So here was S bar. And what we found in that paper with Fellner, Parsons, and Chabold is that this growth sequence, or growth coefficients as we call them, are Chebyshev polynomials of the first kind. So we have this recurrence that Sk plus 2 is S1 times Sk plus 1 minus Sk. Or you can write Sk in terms of this S bar as this polynomial with leading coefficient S to the k, S bar to the k. I mean, that's also true in the finite case, but I'm just not going to talk about that here because the finite case only has 3 options. And we can say more about this. So the sequence of these growth coefficients grows asymptotically, exponentially, if and only if S bar is more than 2, and I should say if and only if it comes from an annulus and not from a disk. And the growth rate, well, the rate at which it's growing in that case is one plus S bar squared minus 4 over 2. And this sequence is constant for all k, if and only if this S bar was already 2, if and only if it comes from the Frieze pattern comes from a triangulation of Sn. Yeah, and because this S bar sort of governs the growth of the whole Frieze, we call this one the growth coefficient, or the whole sequence the growth coefficients of the Frieze. 2 remarks. So maybe I'll copy our example from earlier. As I said, like a triangulation of a polygon of an annulus gives 2 Friezes. So here I've considered this triangulation, and the quiddity sequence was 2, 3, 3. And that's really what we had in the example. I'll try to squeeze everything. So of course I can also study the other quiddity sequence, which has entries 4 and 3. And if we work that out as a Frieze, and please, you have to help, I've not prepared this one. So stop me if there's a mistake. So I do 4, 3, 4, 3, and then I have 12, this should be 11. And in the next 121, 120 by 4. And I won't do the next one. But we can already see what's happening. So here the period was 2. So to compute S bar, I have to go to row 2 and subtract row 0. And row 2 was this one. And that's quite convenient. Row 2 minus row 0 is all constant anyway. And we see S bar is 10. And then you find SK is the same. So the remark is when you have a triangulation of an annulus, you get 2 Friezes because you get 2 quiddity sequences. And they have the same growth coefficients. So if you're familiar with the cluster algebra or even the cluster category side, the story behind that, you know that the triangulation of an annulus gives you a module category or cluster category with some tubes. And in fact, there are 2 tubes here for these 2 Friezes. And this identical growth is viewed as a common behavior of the 2 tubes in these associated categories of type A tilde, as we have worked out in more recent work. If Kanakji, Jacobson, Kulkarni, and Todorov. And the growth coefficients come from certain numbers of submodules in that setting. And that's where I'd like to stop. Thank you.
Yeah, thank you very much for this talk. There's some clapping in the audience. Are there also some questions in the audience? Feel free just to ask the question.
So maybe I can ask a question. All this, the connection to geometry here is only to plane objects, triangulations of polygons and annulus. Is there any kind of connections to 3-dimensional geometric objects, polytopes, or higher dimensional?
Well, no, there's a problem here because like I've tried to do that a lot with 3 dimensions, for example, in a cube. Well, the problem is that the number of elementary, I don't know how you, building blocks is not constant. So whereas in a triangulation of a polygon, you will always have the same number of diagonals and triangles. That's not true anymore. And I think that's a feature we use here. So for some,
maybe you could, so maybe you could have extra conditions on your triangulations of higher dimensional things, which make the numbers of say simplices fixed or something like that.
Yeah, exactly. Yeah, I don't know how to do that. That would be really good. I mean, what we did is we looked at non-planar surfaces, but it's again 2-dimensional because at some point I decided I didn't know what to do with the simplices in 3 dimension. If you take another surface, like with several boundary components, you get a Frieze for each boundary component. But so far we don't know how they're linked. So we don't know whether the growth is the same. And that there is also a lot of questions because we have associated cluster structure, but I don't know how to interpret, say, these numbers in the more complicated surfaces.
Could I just, this is a bit ignorant of me, but I guess that cluster algebras can be associated to triangulations of higher dimensional things, or is it only plain?
Well, some of the cluster algebras, well, they can be associated to coordinate rings of algebraic varieties. And for example, you can associate them to Grassmannians, where if you take Grassmannian of two-dimensional subspaces in n space, then it's triangulations. But then if you go to k equals 3, 4, and 5, yes, you don't work with triangulations anymore. And that was one of the things I tried for, that's why I tried to use cubes first. I didn't know how to make that work. But yes, there are other cluster algebra structures.
So the Grassmannians with k bigger than 2, they are associated to what kind of polytopes? Do you know that?
No, I don't know that. I use Posnikov diagrams for them, which are planar, but not triangulations. So they are given by, like, say, for example, k equals 3, you take 3 subsets of n, or they arise from collections of Blücher coordinates in the Grassmannian, but I haven't used higher well, I guess some people have, but I haven't.
Mm-hmm.
Okay, are there further questions? Maybe slightly related to this question. So I think your annulus is you take the circle and then you put one circle in the middle, right?
Mm-hmm. Yes.
I mean, you could also put several circles, several holes, right?
Yeah.
Would this change the picture, or?
Yeah, well, in the sense that we don't see that, well, we don't see a link anymore between the Friezes. Okay. So we've tried that out in that 5-author project for a bit. It just gives you, like, for every boundary or every circle that you cut out, you get a Frieze. But and in fact, I have for this Grassmannian, this is not, I'm sorry, going back to the other question. We know the Grassmannian gives a lot of tubes, so it would be like a lot of Friezes, but they're also not linked like this very close linking here. So there are 2 ways we can generalize, and we don't know how the growth coefficients are related.
Okay, do we have further questions? If that doesn't seem to be the case here in this setting, I think there's also we can also go to this other room. I guess Kurush sent an email since some